Vahdat. I'm a PhD student here, and I'm going to talk about classification methods in this session, mostly because last time we covered regression methods, and we're going to continue that. So let's see. Okay, so in the last session, we covered the first 4 titles here. We covered how to read the data into R. And if you missed the last session, you can check out the slides in the same folder I shared with you. We also learned about how to pre-process and clean the data in R and how to build linear regression models and making predictions. Today, we're going to talk about classification methods and how to evaluate your own model to see if it's good enough or not. I'm going to come down to the classification methods so we can start there. Okay, so the main difference first between the classification methods and regression methods is in the response values. So if you have a problem that the response or Y variable can only take categorical values like yes, no, or married, not married, or just some integers, for example, only it can take like 0, 1, and 2 values. These are called classification problems. If the response variable is a continuous variable and it can take any value within a range or without any range, it's like house prices or like the length of some piece, and then it's going to be a regression model. So today we're going to focus on classification, and more specifically, we're going to assume that our response can only take 2 values, 0 or 1. This 0 or 1 is just numeric representation of 2 values. It can be anything. It can be yes, no, or whatever you want. And we're going to learn how to build a prediction model for this values. So if you remember from last time, for the regression models, we would fit a linear function to the values using linear algebra. I'm going to go back just to show you what we covered. So for the regression model, we had the response variable, and this response variable were represented as a linear function of your independent variables or your columns in the data. Now, for the classification methods, we cannot assign y directly to a linear function of x values, because this linear function can take any value, and you know that your y can only have 2 values, 0 or 1. So you need some sort of a link function to convert those real valued function to a binary response that you have. For the binomial distribution, which is what we have here when we have only 2 values, you use something that is called logit link function. So logit link function is represented as follows. It's the log of the probability of y being 1 over 1 minus probability of y being 1. And in order to get this probability to convert this value, you can easily take exponential of both sides, and this would give you probability would be equal to exponential of g of y over 1 plus exponential of g of y. So this way you can find the probabilities that each observation is going to be 0 or 1. Now, having this probability, you can set a threshold that usually is half. If the probability is over half for that observation to be 1, you assign it to 1. If the probability is less than half, you assign it to be 0. Now, this half threshold is not a fixed number, so you can find the best value for your data depending on the values that the data takes. And we're going to practice this into our codings. Let's see, let's remove these. Okay, so in order to build this model, we call this model generalized linear model. That's because you're not restricting your linear model to follow normal distribution. You are following binomial distribution here. That's why it's called GLM. There is a function in R that you can directly use, and this is GLM y tilde dot, which we talked about it. It means y with respect to dot means all the variables in the data. And you need to make sure that you set the family to be binomial for the binary valued responses. Once you build this model, you can easily predict with the predict function. This is same as before. The only difference is that you need to assign a type now, because R can predict two things for you. It can predict the probabilities and the responses. But if it predicts the responses, it uses a half threshold as a fixed parameter, which you don't want if your data is not balanced. So you use response to give you the probability here. Okay, now how can we evaluate a classification model? Since we cannot compute the errors like before, so we can say, okay, let's see what was y hat, what was predicted minus what was supposed to be, and then like square it and sum it over. Since you can't do that, you need some other methods to evaluate your classification model. The first thing that is very popular is AUC, or the area under the curve. This metric gives you a measure of how much your model is capable of separating two responses from you. So the plot of AUC is something, if this is the line of x equals y, the plot of AUC is something like this usually, and the more it's and the closer it is to the top left corner, it shows you your model is more powerful in separating zeros and ones together. So this is one way to evaluate your model. The second and the third way that are mentioned here are sensitivity or true positive rate and specificity or true negative rate. These two tell you what is the proportion of the positives or the true values that were correctly selected. And the second one tells you what was the proportion of the negatives that was correctly selected. Now, my question for you guys is that which one do you think is more important for a given problem? You can put it in the chat if you want, or you can speak. You unmute yourself and talk. Yeah. So let me give you an example. Maybe that makes it easier. So if you have predictions here that are either 0 or 1, and the true values here that are 0, 1, if you have 10 here, 10 here, 5 here, and then 10 here, for example. This kind of tables are called confusion matrix. So the columns are the true values, so the actual values of the response, and the rows are the predicted values. Now, you tell me first how we can compute the true positive rate and true negative rate, and which one should be larger, and how would that help?
So I guess you would, for the true positive rate, you would have like, it would be 10 over 10 plus the false negative group, which I guess is 5.
Yeah, so it will be 10 over 50. And the true negative rates are similar too, so it's like 10 over 20. Okay, I'm going to explain the answer because I don't think. So the answer is actually, it depends on your problem. So if you are predicting the chance of someone getting a rare disease, which is going to happen 1 in 100,000 person, I don't know. For that kind of probabilities, you probably want to put more weight in your true positive rate or sensitivity, because if you miss one of those people, that's a bad thing. Because but if you misclassify a person who doesn't have a disease as someone who has a disease, that shouldn't cost too much for the doctors to figure out, okay, that was a mistake and go back. But if someone is missed from the beginning, that's that's the matter of life and death. So it depends on the problem. Sometimes finding the positive ones are the most important. Sometimes finding the negative ones are the most important. And depending on your problem, you need to decide on which one of these two you want to put more weight on. So that's something to keep in mind. Okay. So besides these two, we also have another measure called accuracy. Accuracy is practically just finds it counts all of the true predictions and computes the proportion of all of the true predictions over all of your data. This accuracy might be misleading if you have an imbalanced data. In the same example I mentioned, if your chances of getting a disease into a data set is 1 in 100, 1%, if your model predicts everyone to be 0, the accuracy of your model is actually 99%, but that model has no use for you. So the accuracy can be quite misleading if your data is imbalanced, and you need to make sure that your data is balanced before you use this metric. Okay, cool. Moving on. Let's see how this. Okay, now that we talked about the classification, the linear classification models, let's talk about another non-parametric method that's called classification trees. So why do we call this non-parametric? Because if you remember, in the linear classification models, you have these parameters, these betas that you need to estimate. And this is why this method is called parametric. But in a classification tree, you don't have any parameters, so it's called non-parametric. What does a classification tree does is that it tries to find split points among all of your variables in a way that if you split the whole data based on that value of that particular variable, your whole accuracy is the best. So for example, if the first node is chosen to be age less than 30, that means that if I split my whole data as those people who are older than 30 and those people who are younger than 30, my accuracy, and predict everyone that's older than 30, for example, as unfit, and everyone who's younger than 30 as fit, my whole accuracy is the best among all of those split points through all the other variables. So what classification trees does is that it scans through all variables, all split points, and find the best one, and then moves on from that. For each branch, so when we move down, we call this another branch. So for each branch, it repeats the same thing again. So for this, now for this portion of the data, those people who are younger than 30, let's do this again. Find among all of those variables, all the split points, let's split the data and find out the best accuracy. So it's a very heuristic method, and it's very fast usually, unless you have a huge data. And for this, and it assigns a final value of fit or unfit or 0 or 1 or whatever your response is towards the leaf nodes. And yeah, but as you may imagine, this is, since it's very heuristic, that means that if a value, if a split point was not that good at the beginning, it doesn't mean that it doesn't get better towards the end. So it's only relying on the first node to make the others. So it's highly variable. So every time you build this model, it's going to get another value. So it's not very reliable. To make this classification trees reliable, what we do is that we build random forests. So as the name suggests, that means that we have a lot of trees there. So what random forest does is that it randomly selects a subset of variables through your data. If you have from x1 to x10, for example, random forest is going to select x2, x3, x5, and builds a tree only on those variables, and gives you a prediction for each point. It again repeats the same process for another tree and another tree. We usually build around 1,000 trees in a random forest to make sure we have a robust solution. But the problem with random forest is that it relies on some hyperparameters or some inputs from the user. The first one is the number of variables to select each time, which in R is called mtry. The second one is the number of trees to grow, and the third one is the maximum depth. So how far should each tree go down, which helps if you have a big data and you don't have that much time to spend, like you don't have 2 days to let your algorithm run. So you can set the maximum depth to be something smaller, like 3 or 4. So it doesn't go that deep and it builds shallower trees each time. So it would be faster. So we need to fit for these hyperparameters, which brings the whole other problem of hyperparameter fitting, which I will explain in the code that we're going to use cross-validation to fit these hyperparameters. So this is random forest, and these are the main 3 methods in classification that we're going to practice in our coding next. Now, before we go to the coding part, I also want to mention about how to evaluate your whole prediction model, because I couldn't talk about this last time. And I think it's very important, especially if you're building prediction models for real data. So what is overfitting? Overfitting means that your predicted values are too dependent on the training data set you use. So if I predict every response variable to be the same as the actual one, my accuracy and everything is going to be 100% and the model is doing great. But if the data changes slightly, my whole predictions will be wrong. So that means that you need to add some variance into the model so that it's more adjusted to the unseen data that is your predicted data. And we need to make sure that the predicted response is for the future data, not for the training data. So it's not too much dependent on your training model. So how can we make sure of that? There are 2 main methods for this. One is called criterion based, the other is called sampling based. For the criterion based, you basically compute some measures that statisticians develop for these problems. The most commonly used ones are AIC, BIC, and adjusted R-squared. You can compute these, and based on the value of these metrics, you can decide if your model is overfitting or not. But I'm going to mostly talk about the sampling base, because these criterion based methods, they have many limitations with respect to like what kind of model you use to build the predictions and everything. So they're not the best in most cases. So we're going to only talk about sampling based today. So for the sampling based, I listed 4 examples, which are, I believe, the most commonly used right now. The first one is k-fold cross-validation. Second one is leave one out cross-validation, which is a special case of k-fold cross-validation. Then we have sample splitting and bootstrapping. Okay, now what is k-fold cross-validation? So k-fold cross-validation, for example, here I have a 5-fold cross-validation. What it does is that it builds K or 5 here, folds of data that are non-overlapping. So that's very important. No data is shared between fold 1, for example, to fold 2 or whatever. So they're all non-overlapping. And each time what the model does is that it builds a learning model on K minus 1 folds and tested on the left out fold. And it repeats this for all the folds. So basically, you're making one prediction for each observation because each observation is only left out once. So you build one prediction for each observation and you repeat these K times to get all of the predictions ready. There is another variant of k-fold cross-validation, which is called repeated k-fold cross-validation. And what it does that is it repeats this folding of the data R times. So it adds more variability to the sampling, and that makes your final results more robust. I'm going the wrong way. Okay. Okay. Now, sample splitting is pretty simple. This is what we're going to use in our models today because I wanted something to be fast. K-fold cross-validation can be slow if you don't have that much time. Do it just with sample splitting. Sample splitting is similar to k-fold, but it's similar to 2-fold cross-validation, but the ratios are not 50-50 usually. Usually people choose more data, more portion of the data for training and leave the rest for the tests. So the data is split in 2 parts. 80-20 is the most commonly used. You can use anything you want, but 80-20 is most common. It chooses one portion for the training, usually the big one, and leave out one portion for testing. So it's very simple. So now, bootstrapping is a whole other method, and it actually has very interesting literature behind it if you wanted to read about it. The main difference between bootstrapping and other method is that this time when I'm sampling from the whole data, I'm doing it with replacement. So before, there was no overlap between these folds, and all the data in fold 2, for example, were unique. But for bootstrapping, I'm taking a sample with replacement. So for example, if you have 1 to 5 data points in my bootstrap, which is going to be the same size of my data, which is 5. So I'm going to take 5 points, but with replacement. So I may have 1, then I have 2, for example, then I don't have any 3, I have 4 and 4. And this is my 5 data. So you have repeated data into your training set. This way of sampling makes sure that you keep the same distribution for your training as the one was in the whole data. So it's the theory behind it is that to keep the fundamental distribution of the data same for the training sample, so it carries the same characteristic as the whole data. So you do this for your training, and whatever is left, since it's sampling with replacement, there is going to be at least 1 point left out. So whatever is left is chosen for testing. So 3 here and 5 are chosen for testing. Okay. How do you reduce the bias in sampling of training and testing in sample splitting. Oh, you can do this. So the bias is actually the minimum in sample splitting because you're only doing this once. So, okay, so there is a trade-off between bias and variance. So bias plus variance is always something fixed for each data point. So once you add more variation to something, like if you repeat your sample splitting 10 times, that means that you are reducing the variance of your estimator at the end. Yes, I'm going to answer the next one. So you are reducing the variance of your nth, your estimator once you repeat the whole sample splitting. That's why your variance is going to be reduced and your bias will increase. I'm trying to remove these, but I don't find this. Okay, cool. Let me go back. Okay, so if I do this only once, my variance is high because I only did it once, but my bias is low. But if I repeat this multiple times, I'm reducing the variance, I'm increasing the bias, because now some data points have multiple predictions, and you're taking the average, and that's more probable to get an overfitted value for that data point. Okay. How is the error calculated when using k-fold sampling and bootstrapping? Okay, so for the k-fold sampling, for k-fold cross validation, why doesn't it? Okay. For this one, the error is same as before because you only have one prediction for each point. So basically, after you do this, you have one prediction for each point as you would have if you build your one training model for whole data and then predicted on the same data. So you would take one prediction and you have one prediction here. So it's the same as before. For bootstrapping, there is a chance that you may not get any prediction for some points, but you get some multiple predictions for some other points. What you do here is that you only work with those that you have a prediction for, and you kind of like reducing your data. But if you choose your B large enough, that shouldn't happen. So statistically speaking, that shouldn't happen if you choose your B large enough. So with large B, you have a good chance of having at least one prediction for each point. And for the classification model, you can use a majority vote, or you can use the average of the probabilities as your final prediction for that point. Does that make sense? Okay, cool. Great. So that was bootstrapping. And yeah, that was it. So we can do the coding now. That's fun. I'm going to stop share, and I want you guys to open your R. And we can move to okay. Let me know if you can see this. You can use these little buttons besides your name. I think there's interaction buttons, so I can see if everyone were able to open their R and open the program. Thank you, Danica. Thank you. Let's see. Thanks. Okay, if you were able to open R, first make sure that you clean all of your environment here with this broom up here and clean all of the plots with this other broom up down here. And there is another broom here to clean the console. So clean everything so you wouldn't have any overlap between your last program and this one. And okay. So while we wait for everyone to get their R open, for those of you who have it open, go ahead and run from line 7 to line 19. What these lines does is that it checks if you have all of the packages, and if you don't, it installs it for you, and then it calls those packages. So you have it loaded in your R. I had everything installed before, so I didn't get any error messages. If you get anything here, let me know. Everything good? Okay. If you were able to run these, that's great. If not, just let me know. Next, let's set this destination. This set WD sets the location of your files. So right now, this is my location of files. So change this to your path. So you need it, I don't know what folder you downloaded the data and everything. If you downloaded the whole file from the Google Drive, you just need to give it this path to the set WD so it can find your data. I'm actually thinking that this is not my path. I have to check it. Okay, this is mine. Awesome. So set this one. Great. Okay, I need you guys to use your interaction buttons again and let me know, because I have no idea if you were able to run these lines. Okay, cool. So after you ran these lines, let's come down to line 321, because we don't want to do those regression models anymore. We just want to do the classification model. So let's come down to, yeah, 321. And as we mentioned before, if you want to read in the data that is in the .data type, like here, you need to use the command read.table, and you can set the separator here as well. That is comma for our data set. We are reading a breast cancer data. So let's go ahead and run this line so we can load in the data, and then run head the name of the data, which is BR here, to see the first few lines of the data and check out what the data looks like. So based on the description of the data on the website, I got this data from the UCI website. based on the description, it said that the first column has no predictive value. That means that we can drop this. So we don't need this, the first column. And the last column, which is V10, is our response value. So it tells us no breast cancer, or yes, yeah, breast cancer. So as a practice, I want you guys write line 324 and drop the first column so we can move on from that. I'll wait a few seconds. Thank you, Saul. Okay, so you can drop columns with using a minus sign right next to their index, or you can use dplyr package and use the function select with exclamation point inside to drop using their name. So you have two options. I use the index, so I run this and I drop the first column here. Now you can check out the data again to make sure everything is fine. I can check out the again with BR. Okay, cool. So you see that the first column is gone. Now, the next thing to check with the data is to see if it has any NA values. We can do that with the function any NA, then the data. It's very simple, and it returns a true or false value, and it says false, so yay. It doesn't have any NA values. Moving on from that. Now, the next part is to actually plot a diagnostic graph for the data to see if there are any apparent connections between the data points. We can do that by first factorizing our response value to make sure it's as factor. And then there is a function called ggpairs. It's coming from the ggplot package. And you give it the data set. You tell it that set the colors based on the response or V10. And you tell it that the upper part of the plot, you want it to be densities. And the lower part, you want it to be scatter plots or points. So you run this, it takes a couple seconds. This is a very nice plot if you're doing a report. I really like this in a slide or a report because it summarizes your whole data and it gives you some diagnostics as well to see if there are some obvious connections between the data set. Okay. Can you guys see the Zoom version of the plot? Okay, so as you see, this is very nice. Let me move my camera a little. Okay, so here in this plot, no's are displayed by red and yes values are displayed by blue, and each variable we really knew it well, we could derive a lot of like analysis from just this plot. For example, if I want to say something like, I don't know what V9 is, but it doesn't matter. I can say that based on this V9 values, I can observe that the values for the no value is a lot higher than the values for the yes value. So probably into the diagnostics, we can V9 is going to be important for us because these two values are actually separating from yes to 9. Yeah. And there is another variable called V7. You see that this one also separates the yes from no's pretty well. So this variable probably is going to be important for us as well. And yeah, and you can see different connections and everything here as well. So this is a nice plot. It gives you a lot of analysis tools, especially if the data is something that you've been working on, working with a lot. So okay, I'm gonna close this. All right, now recall that when we looked at the first few lines of the data, we see that there are a lot of categorical variables. For example, V2 is obviously some categories between some number ranges, and V3 is also like that. So what we do next is that we need to convert these categorical variables to dummy variables so that they take numerical values for our model. You can build dummy variables using the function dummy vars, and what it does is that it gives you give it the whole set of data that has these X values, and it returns some data set instead that with a binary variable for each value of those categories. So you run this, and next, using these dummies that you created, also make sure that whenever you use dummy vars, you also use full rank equal true, because you don't want dummy variables for all the category levels, because that way your data is going to be dependent, because always the last category it can be found by like by negating all other variables, all other categories. So if it's not everything else, it's definitely the last category. So you need full rank to drop the last category. And so we create the new data here as well. You can run this. Now, I specifically moved V10 to the end when I'm creating the dummy variables. And let's change the last column name to Y just for our ease of computation. And next time into our diagnostics, we need to check if some of those variables have near zero variance, or basically there are constants. So you can do this using the same function that we did use before, which is near zero var, and run this and see which variables have near zero variance. So you can see a list of the functions, a list of the variables printed down here. If I want, okay, so something that catches my eye is that these values are the dummy variables that we created for each category. For example, here is variable 4 from the range of 45 to 49, and variable 4 from the range of 50 to 54. So basically what it tells me that is the variance in each of these categories is so low that it's considered almost constant. So what I do next is that I'm going to combine these categories together into one category. So I don't need to have two separate variables for 45 to 49 and 50 to 54. I can create one with 45 to 54 and sum these two binary variables together. So I'll do that for all of these variables here. You don't need to do it yourself right now. It takes time to check everything, but basically it creates the new variables using mutate function, and using the select function from deploy R package, I'm going to drop all of those categories that were combined right now. Okay, I'm going to pause here. Any questions up to now?
Uh, do you have my voice? Actually, it's not a question. It's a request.
Yeah.
Kimia. Do you share these, files and recording session with us? Because I just with a delay. And
I shared the files. I can share it again. I think the link of the file is back in the chat. You probably didn't see them.
yeah, exactly. Thank you so
Sorry,
much.
why didn't you say anything sooner? I'm sorry.
No,
So
no
this
problem.
is the files, yeah. Any other questions? Okay. So now that we combine these variables together into one category, let's check again to see if there are any other near zero variances. Okay, we still have one more. So what I do next is that I'm going to combine this to its other category that is next to it. So it's 45 to 54. I'm going to combine it to 40 to 44. And this is the same thing as before. So now that we are in line 367, we can check again and see that there are no near zero variances. Now, this is an exercise for you. Based on what we learned before, you can go back to the code and find these as well. Based on what we learned before, compute the correlation matrix between between all of the variables, and then plot it for me. If you don't know exactly how, go back into the code and you can find some resources there. Okay. Hope you got it by now. Okay. So for the correlation, there is a simple function called core, and all you need to give it is the data set without the response. So what I'm doing is I'm dropping the index of the response since all the data was shuffled before. So I don't know which column is exactly my response. So what I say is that find the column index that it equals to y and drop that. So we can compute the correlation and we can use core plot to plot all of the correlation matrix. All right. So this is a nice plot because you can see the correlation between all of the variables. And what is important is that to look for very dark blues and dark reds. There is one with a dark red that catches my eye here is V6 no and yes. So that makes sense that they are negatively correlated, just to make sure that they do not cause any problem for us later on into the model. I'm going to drop V6 no, just to make sure we don't have any highly correlated variables into the data. All right, now that the data is clean and ready to use, we can actually do our predictive modeling. The first thing we need to do is we split the data. As I said, we don't want to overfit our training data. So I'm creating two partitions of the data based on the values of my response to make sure that those two partitions have the same proportion of the yes and no with each other. So you say create data partition. This is a function in caret package, and you give it the binary vector or your response, which is going to be considered into creating these two partitions, and you tell it that you want 80% of the data to be inside this partition, and this one is just selecting the indices for you. So you also need to set the seed before, so we get the same data as each other. So this creates a training ID. So this is basically data point indices that are assigned for training. All right. Now that we have this training data, we can build a GLM model. So for the GLM model, we have to make sure that we build the model inside train, but we test it over the test. So we build using GLM function with the binomial family, and we can check out the model using the summary. So, okay. You can see that there are some variables that were significant. They have a star here. One is V6 yes, and the other one is V5 between 9 to 7. This tells me that these two variables had high probability in affecting the response. Well, that's good. We can move on to our actual predictions. We can predict the values using the predict function. Then inside the predict function, you need to feed it your GLM model and your test data. So you say, I want to predict over test. I'll do the same for the train data to have the predicted values for test and train both. Why do I need the train data test? Because I want to find out what is the best threshold to divide to set the values of y. So I want a threshold other than half that is well suited for my data, that I can split the data to saying if a response has a value of 1 or 0 based on that threshold. So, okay. For that, what you need to do is you build an ROC model using the trained data response and the trained data predicted values. And you can also plot the AUC curve using the same model. This is our AUC curve. It doesn't look so bad. It has, you see that what I meant. So as the more this top corner is towards top left, the better is the model. All right, now to find the best threshold, what we do is we use a Uden method, which is finds the best threshold that maximizes sensitivity plus specificity. So depending on which one that matters to you, you can change this criteria, but basically what it does is that it gets the thresholds from the ROC model up here, like in the first one, and then it gets the sensitivities here plus the second ones, and it creates a data frame using these two. After creating this data frame, it finds the maximum of this distance, and it selects this as our optimal threshold, which in this case is 0.22. You see how much is different from 0.5, and this affects your final prediction. So this is a good thing to do every time you do a classification model. And We can create a confusion matrix like the one I drew on the slides using the table function. This is very simple. You say all the predicted values, these are probabilities predicted, that are greater than this threshold that we just found, versus all of the predicted values. So this gives you a table that looks like this down below, and the columns are your true value or your actual value, and the rows are your predicted. You see that your true positive is not that good. You're almost halfway wrong. So it's like 10 to 18. And your false positive is not that bad. It's not that bad. So keep this in mind when we are going to compare our other models. You can compare it to these values. We can also compute the accuracy by saying how many of these predicted values that were greater than threshold are actually equal to the actual values, and then divide this by the number of rows of your data. And this gives you 66% accuracy. So you can compute the sensitivity and this hard word that I cannot pronounce using the same table. Okay, so this was the GLM model, which was very simple. I'm going to skip the lasso model. You can run this yourself and find the results. And I'm going to talk about the random forest, which is line 457. Okay. Let me know if you could run everything up to here, and if you're following the logic here.
Actually, I have a question.
Okay.
Can you describe the logic one more time? I didn't get the point, to be honest.
The threshold one?
The table that, you know, compared false, true, one.
Confusion?
Yeah, confusion.
Okay. So the confusion matrix gives you two things. It gives you your predicted values versus the actual values. So what I'm doing here is, let me go up to show you the code. So what I'm doing is that I'm telling R to give me a table of these two values. So the predicted probabilities, this is predicted GLM test, that are greater than the threshold versus the actual values. What it gives me is these false and true, meaning either the predicted probability was greater or not, versus the actual. So if we see 28 in the false and 0 index, that means that 28 of my predictions that were 0, they had actual 0 value. So 20 of the zeros were correctly identified. When I'm seeing 8 here, that means that I predicted these 8 ones to be 0, but they actually had 1 value. And same goes for the rest. Does it make it clear?
Yeah, I got it. Thank you so much.
Okay, great. So let's go down here for a random forest model. Now, as I mentioned, random forest has 3 hyperparameters. The most important hyperparameter in the random forest is the mtry, or the number of variables that it randomly selects each time to build a tree. The remaining ones, you can just choose a large number for them, and they wouldn't make that much of a difference into the performance. So what we're going to do is we're going to only fit the mtry. So first we need to set the seed again to make sure that our results are the same. And These next two lines needs to be done to be able to run the train control and then train function from the caret. So caret requires you, if you have a classification model, that your response variable to be a factor type valued. So we're going to make our response as a, what did I do? Sorry. We need to make this as a factor. Then we need to make sure that the column names of the BR are actually in the type of names. So these two are just needs to be done before the caret functions. You don't need to worry about them. Now, inside the train control, I'm telling what is the control method that I want to use for fitting these hyperparameters. So I'm telling this to use cross-validation the same way I explained. We split the data into folds and use 10 folds for this cross-validation. Then to search through all the values of the hyperparameters, I'm telling it to use a grid method. Grid method basically goes through all of those variables, all of those values that the hyperparameter can take and run it once for them. And the last two parts are just telling the train control to save the predictions that you're making and also return the class probabilities for each class for me. So we build this control function. Then we need to set the seed again to make sure everything's the same. And then I'm going to tell it to make a grid. That's the same grid that is going to being searched through. For mtry, taking the values from 1 to 24. Why 24? Because our data set has 24 variables. So the maximum number of variables that it can choose is 24. You can actually go 23 here because it can't choose the response value. So it says from 1 to 23, try 5-fold cross-validation and report the result for me so I can decide which value of mtry is the best for us. So we make this grid. And next, we use the train function to actually search through this grid. So inside the train function, you have your response and then your training data, because we are assuming that we do not know the test data. And if you use your test data here, you actually are overfitting your model again. And your model is going to be dependent on your data. So you need only training data to set your hyperparameters. You tell it that your method is random forest or RF. And the metric I want to use, since it's classification, I want to use accuracy and use this tune grid that I just defined and use this control function that I defined up here to build your sampling method. It's very simple. And once we run this, it takes a couple seconds to run since it's doing this 23 times. So for each number, it's running one cross-validation. Let's see. Okay, once this is done, we're going to print its result and then plot the graph of the hyperparameters that we fit. It's still thinking. This is why hyperparameter fitting is actually an open research problem, because all we can do is some heuristic methods like this, and they take a lot of time. And my data is very small. It's like 200, 300 observations only. Okay, it's done. So we can print its result to see what it gives us. Let's go up. So what it tells me is that we had two classes, 0 and 1. It adds an X before to make it non-numeric. And it gives an accuracy and a kappa. A kappa is another metric. We can ignore this. It reports the accuracy for each value of mtry. So for mtry 1 to 23, what is the accuracy? And we can simply use the function plot and then this train function we defined to plot the mtry. So in this plot, you see how the accuracy is changing when you are adding the mtry. So based on this, which is interesting because, okay, so it's random. It gives you every different values every time. Based on this, it tells me that mtry 1 is the best, it has the best accuracy. But since mtry 1 can only give you 2 values of predictions because it can only split it once and go down, I'm going to choose either 2 or 3. They're not that different either. So it's 0.78, this one is 0.77. It's not that different. We can choose either 2 or 3. I put 3 here, you can put 2, it doesn't matter. Now that you know what is the best value for mtry, you can actually build your random forest model. First, you need to load the random forest. And if it doesn't load for you, let me know so we can install it on your R. I think it loaded. Okay. So for the random forest, it's similar to GLM. You need to give it the relationship you want to build the model on, which is y tilde dot, meaning the same thing as before. And you give it the training data. So you say the BR data, only the training indices, and select the mtry as the one that we fitted, 3 or 2. You tell it the number of trees to be 2000. I choose 2000 because I want to make sure that it converges at the end. You can choose less number of trees if you don't want 2000. And yeah, we can run this. So it builds a random forest model. It's pretty fast. The good thing about, so random forest, since it's non-parametric, it doesn't give you interpretation like the GLM model. Instead, it gives you variable importance plot. So into the variable importance, it tells me which of these variables had the most impact on the response. In our case, is V6 being yes had the most impact, and V5 being between 9 to 17 and 6 to 8. So now that we have our model, we can do the same things and sorry. Oh, yes, we can do the same things and build the predicted values on the test set and our confusion matrix. Now, this is very interesting to me. And I want you to also notice here because that's when setting the threshold matters. So I predicted using this model and computed the confusion matrix same as before. And what we see is that the prediction versus reference, meaning our actual data, is really bad. It's we're predicting everything almost to be 0. And the question is, why is the prediction so bad? The reason is that what you're doing here when you predict the response using the predict function without setting any threshold, it's going to choose half as its threshold. So it's setting all those values that are greater than 0.5, all those probabilities that are greater than 0.5 to 1 and less than 0.5 to 0. And since this data was imbalanced, most of those probabilities were less than 0.5, but that does not mean that they are 0. So that's why our confusion matrix is so bad. So to fix this, we can actually compute the predicted probabilities and set the threshold using the Uden metric again. So we are going to repeat the same thing. We're going to build an ROC model. From this ROC model, get the thresholds and the sensitivities, and then find the maximizer of this metric. So now after I changed this and computed the threshold it gives me is 0.16, which is even less than the threshold we had before. This gives you an insight of like how setting a threshold matters for classification models. And using this one, now we can compute the confusion matrix again, and look how much it got better. So we have 12 true values. So before, if you remember, we had, let me go up to compare it with the GLM model. Okay, so for the GLM model, we had 10 to 18. The true positive rate was 10 to 18. Now it's 12 to 18. So you see how much it got better. You see that for this improvement, we lost a little of our true negative rate, but that's okay, because again, when you're predicting for an unbalanced data, you care more about those classes that are in the minorities, not in the majority. Yeah, so that's how you build your confusion matrix and how you compute a threshold for setting the predictions. The last thing that I have here is how to plot a tree. This might be helpful for you if you want to give some interpretation of your model for your paper or your report. I'm not going to go through the details. I actually found this online because it's not something you want to do every time. So it uses the library party, and it creates a graph of one of the trees inside your forest or random forest. And it gives you something like this, which can be helpful for, again, just reports. You don't need this for like actual predictions. It just plots one of those trees for you. Okay, so that was it for the classification methods. One other method that is the same as random forest, but it's called bagging, is that if you set the mtry inside random forest to be the same as number of your columns, then it's called bagging, and sometimes it gives you better results. You need to check that as well if you were interested. So I'll pause here for questions.
Yeah, I have a quick question.
Yeah, sure.
Have you done anything with like feature extraction from your random forest models, like being able to see which variables are being selected?
No, but I know that it saves those. Have you, okay. I think within the, let me find it. So within the random forest model that you build, I believe that it saves those steps if you tell it to save the steps.
Okay, yeah, no, I was just curious because I
Uh,
was like
yeah,
trying.
you can,
Yeah.
since they're random and they're over 2000 trees, so the sampling is done 2,000 times.
Mhm.
It probably contains most of the, like, it contains a random range of the variables, but
Mhm.
I believe that, let me check. I know that inside the random forest function, there is a track or like something like that. Here, do trace. So there is a parameters do dot trace.
Okay.
If you set it true, it probably saves you the whole process, and
Okay.
you can find the variables there.
Okay. Yeah, because I
You,
know like sometimes it calculates importance, and so I was thinking of trying to do it that way, but
yeah.
I'll look at the yeah. Thanks.
Yeah, sure. So, Danica, I suggest also you check out these other option inside the random forest function too. It's called keep forest. They probably going to let you like save every step.
Cool.
Okay. If there are no other questions, you can call it. Thank you, guys.
Thanks, Kimia.
Yeah, of course.
Thank
Thanks.
you, Kimia. It was really informative session.
Thank
It's
you.
really appreciated. Have a wonderful weekend.
Thank you. You too.
Thank you, Kimia.
Thank you, Sam. Sam, do you mind hanging out a little after?
Yeah, sure.
Thanks.